Presentation will go over kinetic molecular theory, which applies to ideal gases. Our objectives will state the postulates of kinetic molecular theory, and we'll use the theory's postulates to explain gas laws. There are 5 postulates to the kinetic molecular theory of gases. 1. We assume gas molecules have no volume compared to the distance between them. As an approximation, we say that the volume of the gas is 0, and we attribute the entire volume to just empty space. 2. Gas molecules are in constant random motion, only changing direction when they collide with something. 3. The average kinetic energy, which relates to the speed of the molecules, is proportional to their absolute temperature. Note, I said absolute temperature. We're talking the Kelvin scale, which is why we use absolute temperature in PV equals nRT. Number 4, collisions of gas molecules with the container result in the pressure exerted by the gas. And number 5, each molecule acts independently of the others. They are not attractive or repulsive forces, which means that their collisions are elastic. They don't lose energy when they collide. Let's try to relate one of the gas laws back to our 5 postulates. So, explain how kinetic molecular theory predicts Boyle's law. Boyle's law is that pressure is inversely proportional to volume at constant temperature with constant moles. Take a moment and see if you can figure this out based on the postulates to the right. According to postulate 4, collisions of gas molecules with the container are the cause of the pressure. We recall that pressure is due to the force of collisions over an area. So when we compress a gas, making the volume smaller, the number of collisions between the gas and the container per area will increase. If we haven't changed the temperature, the force of those collisions must remain the same. That's kinetic molecular theory postulate 3. Therefore, the pressure must rise. The book gives explanations of Amundsen's law, Charles's law, Avogadro's law, and Dalton's law as well. I recommend reading through them and making sure you understand how to apply these concepts in different scenarios. We can also relate molecular speeds to kinetic molecular theory. This graph is of the Maxwell-Boltzmann distribution. It will come up somewhat frequently to explain the relationship between molecular speeds and lots of different things. Here, we're going to relate it to kinetic molecular theory. So first, we need to define what we're looking at. The Maxwell-Boltzmann distribution describes the number of particles versus the speed of those particles. This distribution applies to any collection of particles, but is usually used to describe gases. You'll note that this graph includes distributions for 3 different temperatures, 100, 1200, and 3000 Kelvin. The range of particle velocities increasing with increasing temperature, and the amplitude goes down. So we have the same number of particles in each of these. There are fewer particles at any given speed as you raise the temperature because there are more possible speeds, but they're the same number of particles. So this graph is labeled with 1s, 2s, and 3s on each curve. 1 corresponds to the most likely speed, or the mode. 2 corresponds to the average speed, or the mean. And 3 is the thermal speed, or the root mean squared velocity, which means that you add up the velocity squared for each component, and then you divide by the number of velocities possible. Anyway, the root mean squared velocity is where we get the temperature of the material. Kinetic molecular theory tells us with postulate 3 that the speed of the gas molecules is proportionate to the absolute temperature. Therefore, temperature is the average kinetic energy. Okay, so kinetic energy is equal to 1/2 m times velocity squared. We don't use the average velocity, meaning the mean, like we normally calculate. Instead, we use the root mean squared velocity given by the square root of 3 RT over m. Note that the molar mass and the velocity are inversely proportional. Therefore, the average speed of helium will be greater than the average speed of oxygen because oxygen is heavier than helium. We can use these results to find the average speed of any gas at any temperature. Okay, and I've done a little bit more algebra here where I've plugged in the root mean square velocity for the U, and then I have simplified the equation. At any given temperature, all gases have the same kinetic energy. Now, that being said, their distribution of speeds will vary based on their molar mass. Since molar mass is inversely proportional to speed, when you increase the molar mass of the gas, you're looking at speed going down. When you do that, so does the range of possible velocities that the gas particles can have. So you can see that from this graph. Helium, which is the lightest noble gas, has a wide distribution of velocities. But xenon, which is the heaviest that we have on this graph, has the smallest distribution of velocities, and it has the lowest root mean square speed. Let's try a calculation. We're going to calculate the root mean square velocity of hydrogen sulfide, the stuff that makes farts smell. We'll do that at 22 degrees Celsius and at 40 degrees Celsius. We're going to sketch an approximate curve for the molecular speed distributions. So this will be an imitation of the Maxwell-Boltzmann distribution from before. So I am looking over here and I see that I have the relationship between root mean square velocity and temperature, as well as molar mass. And I'm going to go ahead and plug in R of 8.314 joules per Kelvin mole, because we want things to balance out and give us meters per second, and that's where we're going to get it. The molar mass of hydrogen sulfide is 34 grams per mole, but joules is in kilogram meter squared per second squared. So I need to use my mass of hydrogen sulfide in kilograms per mole. And finally, my temperature needs to be in Kelvin so that my units work. So I go ahead and I plug in my R and my molar mass in kilograms per mole. So we just divided by 1,000. And then I calculate the T in Kelvin. So that's either going to be 293.2 or 311.2. When I plug those numbers in, at 22 degrees Celsius, I get an average velocity of 470 meters per second. And at 40 degrees Celsius, I get a velocity of 486 meters per second. So now we're going to try my attempt at the Maxwell-Boltzmann distribution. So we've got the number of particles here. And we have the speed. And we know that we're going to have 2 points along this curve, the 470 and the 486. Not the most perfect, but it will function. Now, if you remember, our root mean squared velocities were not actually centered around the average speed. They were on the going down part of the slope. So I'm going to do the one at 40 first. We'll note that I'm going down. It's not going to be perfect because I'm not great at drawing, but we'll hopefully get the idea. And then I'm going to do the one at 470, and we'll notice that it is not as wide. And if I were being better at this, I would do that. Okay, so we have an approximate Maxwell-Boltzmann distribution. We can see that we are shifting to the right and lower. To summarize, we have 5 postulates. We assume that gas molecules have no volume compared to the distance between them. Gas molecules are in constant random motion, only changing direction when they collide with something. The average kinetic energy, which is related to the speed of the molecules, is proportional to the absolute temperature. Collisions of gas molecules with a container result in the pressure exerted by the gas, and each molecule acts independently of the others. There is no attraction or repulsion, and their collisions are elastic. We also have multiple equations here. Kinetic energy is equal to 1/2 mv squared, or u squared, sorry. Root mean squared velocity is equal to the square root of 3RT over m, where m is molar mass. Kinetic energy, if you put in the average, is 1/2 molar mass times the root mean squared velocity squared. And that means that kinetic energy average is equal to 3/2 RT.